Welcome everyone. Today we're going to be going through questions 20 to 30 on the 2005 Intermediate Australian Maths Competition. Here's question 20. We have PQRS, which is a parallelogram. L is a point on the side PQ such that PL equals 1 and LQ equals 2. M is the point of intersection of PR and OS. And then we need to find the ratio PM to MR. So first we can calculate SR, which is just 1 plus 2, so 3. Now we can see that these two triangles are similar from angle, angle, angle equal. So now we just use the ratio of similar triangles, and we can get that PM on MR equals PL on SR, which is 1 over 3. So that's our answer, A. Question 21. A train leaves Canberra for Sydney at 12 noon, and another train leaves Sydney for Canberra 40 minutes later. Both trains follow the same route and travel at the same uniform speed, taking 3.5 hours to complete the journey. At what time will they pass? So here I have a Canberra, and this train got a 40-minute head start going that way. And here's Sydney, which does not have a head start going this way. So I let V equal the speed of both trains, which is the same, and S equals the displacement starting at 1240. So now we have that the Sydney train travels a distance after 1240 of VT from Sydney going this way, and the Canberra train at time T will be a distance of VT plus the head start of 40 times V. Now the distance all the way between Canberra and Sydney is 210 V, because 3.5 hours is 210 minutes. The distance between Canberra and the Canberra train is just VT plus 40, and the distance between Canberra and the Sydney train is going to be the total distance between Canberra and Sydney minus VT. Now we can equate these two. So VT plus 40 equals 210 minus VT. Next we can factor out V in both of them. Then the V's cancel, and we have T plus 40 equals 210 minus T, so 2T equals 170, and T equals 85. This means that they pass 85 minutes after 1240, which is at 2:05, so we get the answer C. Question 22. The number of 5-digit numbers in which every 2 neighboring digit differs by 3 is, and then they have the options. So I didn't really like this question because the way you solve it is kind of just counting all of them. But the tricky ones are just 3, 6, and 9. Then you'll see that every other number other than 3, 6, or 9 is going to have 4 each. So if we add all of these up, the totals, we get 8 plus 5 plus 5 plus all these 4s, giving us 45 total. I also wrote some Python code to verify this, just going through every 5-digit number, and then checking if they all differ by 3, and counting these, and it gets 45, all these 45 numbers here. Okay, next question, 23, good geometry one. We just need to find the area of the shaded rectangle. So again, we have some more similar triangles we can work with. All of the outer 4 triangles are similar. So first, let's solve for this length here. We have x on a half equals a half on 1, so x equals a quarter. Now we can solve for this length. So this whole length is 1, so this is just 1 minus a quarter, so 3/4. Now we can solve for this length using similar triangles again. So we have x on a half equals 3/4 on 1, and if we solve this we get 3 on 8. So now we can use Pythagoras to calculate the length and width of the triangle. So for the length we have L squared equals 3/4 squared plus 3/8 squared. We can square both the numerator and denominators. Then 9/16 plus 9/64 is 45/64. Take the square root. The square root of 64 is 8. And then we can factor 45 into 9 times 5. And we get L equals 3√5 on 8. We do a similar thing for the width. This time with a half and a quarter. Take the square root and we get √5 on 4. Now we have the width and the length. There is just width times length. So that's √5 on 4 times 3√5 on 8, which gives us 7.5 on 16. And this is exactly halfway between 7/16 and 8/16, so our answer is D. Question 24. A 3x3 square is divided into 9 1x1 unit squares. Different integers from 1 to 9 are written into these 9 unit squares. Consider the pairs of numbers in the squares sharing a common edge. What is the largest number of pairs where one number is a factor of the other? Again, I didn't really like this question because it's a bit of trial and error, but there is a trick we can use to make it a bit easier. So the total number of adjacent pairs is going to be 12. And the question asks the maximum number of pairs where one number divides the other, but we can find the opposite. Related to this is the minimum number of pairs where one number does not divide the other. So I'll solve this instead, and again, trial and error, we see that 2 isn't really possible, but I found one example, and there's many, where you can have a minimum of 3. And then if the minimum is 3, then the maximum where one does divide the other is going to be 12 minus 3, giving us 9. I verified this with Python again, getting all the pairs, the adjacent pairs, checking if either divides the other, and then counting them up. And the maximum was 9. Question 25. The polygon shown has a reflex angle at P. In a polygon with n sides, what is the largest possible number of reflex angles? So this was an interesting question, bit of creative thinking. We can actually form a kind of circle here, or close to a circle, and all of these are going to be reflex angles. And then we just have this triangle here, where there's 1, 2, 3 acute angles, giving n minus 3. Question 26. My name is Lewis and my father has cooked me an L-shaped cake for my birthday. He says that I must cut it into 3 pieces with a single cut, so that my brother and sister can have a piece too. So I have to cut it like this, or this, but not like this. Because this is only 2 pieces. It has to be 3 pieces. He says that I have to be polite and let them have the first choice of the pieces, but I know they'll be greedy and leave the smallest possible piece for me. So I want to cut the cake so that my little piece is as big as possible. If I do this, how big will my piece be? So here, this is the optimum solution, where the area of piece A is equal to the area of piece C. So let B equal the base of the triangle here, and then from these similar triangles, we can calculate B on x equals 20 on 10, so B equals 2x here. So now the area of piece A is half times base times height, just area of a triangle. So the base is 2x and the height is 20, so the area is 20x. The area of piece C here, if we cut it here, then this rectangle is going to have an area of 10 times 10x, and this triangle here is going to have an area of a half times x times 10. And then if we expand this out, that simplifies to 100 minus 5x. And now we want where the areas are equal, so we let 20x equal 100 take 5x. Solve this, and we get x equals 4. And now we can sub this into either of these. I just did piece A. So 20x becomes 20 times 4. So the size of his piece is going to be 80 centimeters squared. Question 27. A supermarket has 7 checkout lanes. All 7 checkouts accept cash payments, but only lanes 1 to 4 allow credit cards. Kath, Kim, and Sharon are all shopping, and Kim insists on using her credit card, but Kath and Sharon intend to pay cash. In how many ways could they choose their checkout lanes? More than one could choose the same lane. So that makes it easy. Kim can choose 4 lanes, and Kath and Sharon can choose 7, and since order doesn't matter, we just do 4 times 7 times 7, giving us 196. Question 28. Each point on the 4 sides of a 1 by 1 meter square is colored one of n colors, so that no points are exactly 1 meter apart. Exactly. No points exactly 1 meter apart are colored the same. What is the smallest n for which such a coloring can be made? So this was quite a tricky one, and it turns out if you color this exactly like this, then you can do it with just 3 colors. So that's the answer, 3. With the single lines, double lines, and triple lines as different colors. Question 29. A regular octahedron has 8 triangular faces and all sides are the same length. A portion of a regular octahedron of volume 120 centimeters cubed consists of that part of it which is close to the top vertex than to any other one. In the diagram, the outside part of this volume is shown shaded, and it extends down to the center of the octahedron. What is the volume in cubic centimeters of this unusually shaped portion? So the entire volume of the octahedron is 120 centimeters cubed, and then we want the volume of this shaded area. And if you look at it, you can kind of see that the entire shape is made out of 6 of these, 1 on each corner. So we do 120 divided by 6, giving us 20 centimeters cubed is the area of this section. Now for the final question. A positive integer is equal to the sum of the squares of its 4 smallest positive divisors. What is the largest prime that divides this positive integer? So we have to analyze some contradictions to deduce some things about what 4 divisors it has. So 1 is obviously a divisor, since 1 divides everything. And then we can deduce that 2 is a divisor, since the integer cannot be odd, because the divisors would be odd, and the sum of squares even, which is a contradiction. Then we know that the next divisor must be a prime p, and since the sum is even, the next divisor is going to be 2p. So if we do 1 squared plus 2 squared plus p squared plus 2p squared, we can get this into 5 times 1 plus p squared. So that's the positive integer, and since it factors out with a 5, then 5 divides it, so this prime p must be 5. Now we can sub p equals 5 back into this, so 5 squared is 25, 25 plus 1 times 5 gives us 130, so that's the number, and then the largest prime that divides 130 is just 13. I also wrote some Python code to analyze this, and it does give, I searched the first 10,000 numbers, and only 130 was equal to the sum of the squares of its 4 smallest positive divisors, which is pretty interesting. And that's the end of the video. Thanks for watching.